let's get started with this question 1. So this question is about electrolysis. So it's about electrochemistry. During the electrolysis of dilute sulfuric acid, so we know in a dilute sulfuric acid, we have H plus and OH minus as a result of the presence of water. If you have learned Kw, which is water dissociation constant, you will know that whenever you have water, you have H plus and OH minus as well. And then of course you have the contribution from the sulfuric acid itself. There's the H plus and SO42 minus. So you apply a current of 0.75 ampere. You apply for 90 minutes and you will get oxygen gas because this is an electrolysis. This is an electrolysis where you use electricity to break down the chemical bond, which is actually the covalent bond, into the constituent elements, and this will give you a ratio of 2 hydrogen is to 1 oxygen. Okay, so this is the volume of oxygen, well, volume of gas, where this line represents volume of oxygen against the time in minutes. So it's a direct proportional relationship. So at 0 minute, that means when at the start of the reaction, at the start of the electrolysis, when you did not apply any current, no electrolysis, therefore no volume of oxygen being produced. All right, so that makes sense. Give equations. So you gotta give equations. So there's plural there. The reactions that occur at each electrode. So you have cathode. Cathode attract cations. Cations are positively charged. This makes cathode negatively charged. Reduction happened at cathode, so red cat. And then you have anode, and anode attracts anions. So anode itself is positively charged. So you need to think about which ions get preferentially discharged and which ions go to where for the cathode and the anode. So at the cathode, where reduction happens, we would think about cations going there, and thinking about the constituent ions that are present in dilute sulfuric acid, the only cations would be the H plus. So H plus goes there. Reduction is gain of electrons, so oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So you gain electrons and you form H2. So you need 2 H plus, and you need to balance out the plus 1 times 2 give you plus 2. You need 2 electrons to balance out the charge to give you hydrogen gas as a molecule, which has no charge at all. And then you have the anode, and anode being the positively charged. And looking at the OH minus and the SO42 minus, your GCSE, IGCSE or O-level, even your data booklet from your theory paper would have told you that the hydroxide get preferentially discharged than the SO42 minus. Preferentially discharged meaning in this case it prefers to undergo oxidation based on the E0 value more than the sulfate ion. Alright, so we have the OH minus. Do I have the OH minus? Not technically. I will have the water, and then I will give you O2 plus H plus electrons. So my H plus is a result of the H plus they float around. Okay, so I will have 2 H2O because I need 2 oxygen. I will have 4 hydrogen. And looking at it, no charge, 4 times plus 1 will need to be balanced out by 4 electrons. Such that when you add the two together, when you add these two equations together, this is 2 electrons, this is 4 electrons. So what you could do later on is you could multiply this by 2, and then this becomes 4 and 2. When you add up the 2 equations together, you get 4H plus 2 H2O plus 4 electrons, and then whatever is on the right hand side, you get that. And I hope you can see that the 4H plus and the 4H plus exist on both sides of the equations, so they get cancelled out. The same thing with the 4 electrons as well. So overall your equation really is just electrolysis of H2O giving you H2 and O2, as I have shown you earlier. Okay, so this is definitely a redox equations because this involves oxidation and reduction. They are not asking you for the full equations. I have just shown you the full equation there to convince you that the half equation was correct in that sense. All right. So balance equation, balance charges with the electrons as well as the H plus, and that should be all right. On the graph above, use a ruler, so you don't want to freehand sketch. Draw and label a line for the volume of hydrogen. So you need the volume of hydrogen, so you need to label as well. That will be given off. So based on the combination of the equation that I show you, they give me this equation. The volume of hydrogen produced is double the volume of oxygen produced. So if this is the volume of oxygen produced, the volume of hydrogen produced will be much more for the same given of time. All right, so I expect the line to be above the oxygen and it will go up. So obviously I don't have the space there, so I'll just have to draw up until the y-axis 250 is reached, and then it's assumed that it goes on and on and on. All right, so the easiest thing really is we know that it doubled the volume of oxygen. The easiest thing I could see here, this is a bit hard, this is quite nice. So this is 50, this is 60, so this is 55. So 55 times 2 is 110, so this must be the hydrogen here, 110. And then for the 40, you have 110 times 2 is 220. So 210, 220 is there. So I'll also start from 0, 0. And you can see my line was very badly drawn, but now it's alright because I'm drawing on the screen. Ideally, you should have a ruler and you have to draw a straight line like this. And then you can label this volume of hydrogen. The reason for me not labeling it inside the graph, unlike this one where it labeled inside the graph, but you can see the background has been changed to white here, so it overlapped the grid line as shown there, and it's quite clear because the background is white. If I write here, I don't have that luxury of the white background, so whenever I try to label something, avoid labeling inside the grid line itself, because it's very difficult to read when it's in between the grid line, unless it's just a coordinate where you just use crosses to represent the point itself. But wherever possible, always label where you have a white contrast background where it's quite clear and easily seen. All right, so that bit is done. And then on the graph above, use a ruler to draw and label a line for the oxygen. Predict the volume of oxygen that will be produced if you use 0.45 ampere instead of 0.75 ampere. So the original experiment is for the 0.75 ampere. So this is 0.75 ampere, that's the volume of oxygen produced. It's trying to ask you to indicate or to predict what's the volume of oxygen that will be produced if you use lesser current. So lesser current would mean, well, less current that flows through the electrolysis or electrolytic setup, and that means you will get lesser electrolysis with lesser current, and therefore you will get lesser oxygen being produced. So it's a direct proportion. So if I look at it, 0.45 over 0.75, so I'm just looking at the ratio by how much it will be decreased, and that gave me exactly 0.6, which is exactly 3/4. I don't need a bracket. Bracket will mean multiply. This is actually 3/5. All right, so whatever volume I produce here, the volume is 250. So 3/5 of 250, 3 over 5 of 250. So 3 over 5 of 250 cm3. This is at T is equal to 90 minutes. So obviously at 0 time, the volume produced will still be 0. Okay, so I just need 2 points to draw a straight line. Okay, 3/5 of 250 give me 150 cm3. So I will expect at 90th minute, I will have 150 cm3 then. And of course, I also start from 0, 0 because, oops. Yep, so there's a straight line. Also start from 0, 0 because at time 0 when no current passes through, I obviously don't have any gas being produced as a result of electrolysis. So this is, I'm gonna have to label this. This is A part 3, okay? So this is A part 3. This is 0.45 ampere volume of oxygen being produced, all right? So during the electrolysis of potassium butane diOH, so this is a diOH anion. They show you the equation. You would form ethene molecule. So this is ethene. You will form carbon dioxide as a result of you losing this bit there. Carbon dioxide, 1 carbon dioxide, 2 carbon dioxide, so 2 carbon dioxide. And you get the H2 as a result of, I suspect, from here. And the OH minus come from here as well. And leaving you the counter anion K plus, therefore you get KOH from there as well. Okay, so you can carry out an experiment to confirm the above equation. So this is the reaction that occurs, and you want to confirm that you actually follow this equation that's given in the question. Okay, so in order to do this, you need the amount meaning the moles. Okay, the mole of hydrogen, ethene, and carbon dioxide need to be measured. So ethene is a gas at room temperature and pressure. The same thing is true for CO2 and H2. So we are measuring the volume of gas being produced. Hydrogen is produced at 1 electrode, and that's not too surprising. They will be at the cathode. Okay, as a result of the H plus present in water. Okay, being reduced to give you the hydrogen at the cathode, where reduction happen. Cathode attracts the cations, the H plus, which gain electrons, as shown in the previous equation earlier in the question. In the previous part of the question earlier on. Ethene and carbon dioxide are produced at the other. The other refers to the anode. The anode attracts anions, which are negatively charged, so anode itself is positively charged. Now you have carbon dioxide and ethene, which can be separated. You absorb it in an alkali, and then that will absorb CO2, because CO2 is acidic oxide, but ethene itself is not acidic or alkaline. Okay, so using the power supply shown below, this is the negative terminal. So this will be connected to the cathode. This will be connected to the anode. You need to draw a fully labeled diagram. How do you measure current? So you need an emitter. So an emitter has the circuit symbol A, like this. The hydrogen produced could be collected. So how the hydrogen produced could be collected and its volume measured. So you need something that will measure the volume. So you will need like a graduated gas syringe. You could also use a burette, like inverted burette, but we have thought that a gas syringe is probably a lot easier. How the carbon dioxide could be removed using a NAM alkali. So I could use aqueous. Do I want to use aqueous? Yeah, aqueous NaOH would be fine, I guess, because the water itself wouldn't give you the gas. So I suppose I could use aqueous NaOH. I could also pass it through a solid NaOH, which would be no problem, except that solid reacting with gas would be slower than solution with a gas. All right, where I could bubble the gas into the solution, there will be a lot faster reaction. All right, the volume of ethene could be measured, again, graduated gas syringe. Okay, so one way I could be thinking about is that emitters could be on the left or on the right, does not matter, as long as you connect something to the emitter. All right, and then I can have I want to do electrolysis, right? So I can have a electrode there, and then I can have something like this. So it's not a very well drawn diagram, plus I'm not an artist, but what I could do is I could draw the best I could. Now I need an inlet, and then I need something that goes out, something that goes like this, and then I need the thing to go in there. So I can use an inert electrode such as platinum. So platinum electrode, this will be a negative terminal because there's the negative there. Negative terminal will be the cathode, because cathode attracts cations, which are positively charged, which means that my gas, I want that level to be lower than that, which means that, so there's my solution there. So there's my electrolyte. And what was my electrolyte? H2O and potassium butane-diOate. So potassium butane dioate plus H2O. Okay. What else? This will be the H2 gas, but I also want to collect the H2 gas. Remember, H2 gas, you need to collect it and you need to measure the volume. So what I could do is I could connect it to a gas syringe, and just a typical gas syringe would be graduated like this. Okay, so this is the graduated gas syringe to collect H2 gas. All right. What else do I need? So on the other side, I will have ethene and carbon dioxide being produced, and I need a setup that will enable me to pass the gas through. So I want to pass it inside. So it needs to be fully absorbed into the aqueous NaOH or aqueous KOH, which is the alkaline solution, which I just named. And then of course, I also need to gas to be bubbled off. And these gas that are being bubbled off is the one that are not being absorbed, by what do I say this? They are not being absorbed by the alkali. That means this is the ethene gas. All right, so I need a stopper like this, I guess. Yep, that should do. So there's the piston there. I also need it to be graduated gas syringe, and this will be the one that collects ethene or C2H4. And of course, this thing there is gas collection, so I need it to be sealed, okay, airtight. So this is airtight stopper, so you don't want to have any opening, otherwise your gas will just escape. So the CO2 and the CO2 and the ethene will pass through there, and they will absorb the acidic CO2. Ethene gas will not be absorbed, and it will get passed through, and it will be measured. It will be collected and measured, volume measured by this graduated gas syringe, and you only need to measure the volume of ethene, not the volume of carbon dioxide. My circuit is complete. I've got my electrolyte, I've got my emitter connected in series, and there's the negative terminal, so this is the negative, this is the positive terminal, so that's the anode. All right, so yeah, I think that's it really. So reasonably generous for the 5 marks. If you read through the questions and you address them one by one, think through them before you actually start doing, otherwise it defeats the purpose of actually planning an experiment. Okay, now what measurements do you need to take when you carry out this experiment? So remember that you wanted the emitter, so the emitter measure the current that passes through the electrolysis setup. Okay, time taken for when current was applied. So from your previous graph, right, you need the volume against time. So if you don't know what is the volume produced at a specific time, then it's not going to be worth it, is it? All right, so you need a stopwatch in order to measure the time taken for as long as the current was flowing. You collected the volume of hydrogen gas, which exists as H2 gas. All right, you also collected the volume of ethene at the other end, the ethene, which is C2H4, which also comes out as a gas. As for the CO2, the CO2 was being absorbed by the alkaline solution. So what you could do, if you use a solid, it's a lot easier to measure the mass, but it's not impossible. I guess you can measure the mass of the alkali before you absorb the CO2. The mass of the alkali alkaline solution, I guess. In my case, because I didn't use a solid, I use a solution, plus tube before absorbing CO2, and of course the mass of the alkaline solution. Because if I want to measure the mass of the solution, I obviously need to have it in a tube or in a beaker. Yeah, okay, so it makes sense that I have to take into account that as well. I can't just pour it onto the balance. All right, but before and after will tell me what is the mass of CO2 that has been absorbed. All right. So the next bit of the question is a bit of algebraic expression. So instead of using actual value, they want you to express it in terms of this kind of algebra terms. So C coulombs of electricity. So this is the charge, or Q equal to IT, resulted in V cm cube of hydrogen gas. So what is the number of coulomb that will be required to produce 24 dnq of hydrogen? So V cm cube, you need C coulomb, alright? So C is coulomb. Actually the unit of coulomb is also C, so I don't want to write the unit there, okay? Otherwise I would have. And then this is 24 dm cube, whereas previously V was in cm cube. So I'll convert the dm cube to cm cube, and then it's a direct proportion. To get higher volume, I will need the higher amount of charge. So that is divided by V. So my expression will be 24,000 C over V, where the C is not the charge, as in it's not what I'm trying to say is that it's not the unit, but it's the value of the coulomb of electricity that passes through. Alright, and the unit will get cancelled out because this is in cm cube, so this is also in cm cube, so it's not like dm cube over cm cube. That wouldn't work. Yeah, so N is that number of coulomb. In terms of N, what is the number of Faradays? Number of Faradays of electricity that will be required to produce 1 mole of hydrogen. Okay, so 1 Faraday of electricity is 96,500. So 96,500 coulomb. So I don't want to write the unit to avoid confusion. So this is in coulomb. This is also in coulomb. Okay, because the unit of C there is in coulomb. So 96,500 coulomb is 1 Faraday. So 24,000 C over V is, which is N. So that is 1 time N over 96,500. So N is basically this whole thing. I could use in terms of N as the question instructed. So that is the number of Faradays that are required. Okay, so give the equation for the reaction that takes place when the carbon dioxide is absorbed by the alkali. So I've used NaOH. I have used alkaline solution of it. So you have aqueous because they also that symbol. If you have used a solid sample of NaOH or KOH, then you have solid. It really does not matter because it's just a matter of you following through your own planning. Okay, not other people plan, but your own plan. So this is the acid. This is the base or the alkali, and the salt that you will get, because this is a neutralization. So the salt that you will get will be a carbonate. You will get sodium carbonate, Na plus CO3 2 minus. The lowest common multiple, primary school mathematics, I don't know, primary 3, primary 4, LCM, between a 1 and a 2 is 2. So it means that you need 2 of the Na plus to balance out the minus 2. That's why the formula of sodium carbonate is Na2CO3. You will get water as a result of neutralization, as there's a hydrogen floating around. You need 2 sodium here, so you must have 2 NaOH. And I will have stat symbol. This is aqueous because they also ask for stat symbols, and H2O is just liquid. What else? The CO2 give me the CO2, so I have 1 extra oxygen, and the 1 extra oxygen come from there. The other oxygen goes to the O there. The 2 hydrogen goes to the 2H there. Therefore, this is the balance equation with the correct identification of the formula of the salt being formed and the formation of water as a result of neutralization. The next bit of the question, which is the last bit of this section 1 on electrochemistry planning kind of question. Predict the organic product that will be obtained at the anode. Instead of using butane diolate, you use hexane diolate. So this is 6 carbon. So butane diolate, just now you get 18 and you kick out 2 CO2. So this is 4 carbon, you get 2 carbon alkene and you get 2 carbon in the CO2. If you have 6 carbon, you can imagine that the end bit, the COO minus and COO minus, will also give you 2 carbon CO2, and therefore you will get you will be left with 4 carbon alkene. So a 4 carbon alkene would mean that actually this is a bit tricky. This is actually very tricky. Let me try and visualize it. So like this, 1 2 3 4 5 6, like that. Okay, so this bit there will give you the CO2. This bit here will give you the CO2. So what actually happened? So as I mentioned earlier on, right? So you get a 4 carbon alkene. Just like in the previous case, you get the formation of only 1 carbon double bond. This is a 2 carbon alkene. So you will get a 4 carbon alkene. You get 2 CO2, 2 CO2 plus a 4 carbon alkene plus But this 4 carbon alkene would not simply have a double bond at the end there, because it's both ends being chopped. So what actually happened is your double bond will be between carbon 3 and carbon 4. So what you actually get would be either this, or in fact a mixture. Okay, because they can isomerize to give you either the cis or the trans. But what we can be sure is that the organic product is a 4 carbon alkene. Therefore, I can be sure that it's a but2-ene. But what I cannot be sure is that whether it's cis or trans, because both could ideally be formed, because you started from a single bond and now you are forming the double bond. So there's no preference for whether you form the cis or the trans in this case, because it's electrolysis and not like a directed chemical reaction, organic transformation in that sense. Yeah. So that marks the end of this first question of this paper 5. Moving on to the next bit, which is I assume will be the analysis and evaluation part of this paper 5. So this is a bit to do with ionic equilibrium. This do acidity, this weak acid, is it a weak acid? No, we don't know whether it's a weak acid yet. It's just this HX. Monoprotic is also known as monobasic, means that one molecule of it reacts with only one molecule of one OH minus. So it's got only one H plus to give away. So you titrate this acid against aqueous sodium carbonate. So carbonate can react with acid to give you salt, CO2 and H2O. That's something you have learned from your lower secondary science many years ago. All right. So the endpoint of this titration is reached when you have this much of the aqueous sodium carbonate. So write the equation for complete neutralization of the acid with the sodium carbonate. Sodium carbonate, as I shown you, I'm not sure if I showed you earlier. Did I show you earlier? Na plus CO3 2 minus. Not here. I think it was in a. Oh, actually, I did show you earlier. There you go. Na plus CO3 2 minus. Unless you know your formula of ions, then you will have problem creating formulas every single time. So you gotta master your basic first. Yeah. As I mentioned, you get a salt. The salt here would be, this is a HX, so it's a H plus, meaning to say it's a X minus. So it has to be Na plus X minus. And then you get CO2 and then you get H2O. They don't tell you to balance it, but whatever equation you write, even from O level or A level or IB or whatever equation you write has to be balanced. So 2 Na there, so you need 2 NaX, and the fact that you have 2x would mean you need 2 HX. Now there's 2 hydrogen, it goes to the 2 hydrogen there. CO3 give you the CO2 with 1 extra oxygen going there. So this equation is balanced. So how does this equation show the concentration of HX is that? So you know the mole ratio from here, and you know the volume of the sodium carbonate required, and you know the concentration. So you know the mole of the sodium carbonate. You know the volume of the HX, therefore can you find the concentration of HX based on this, and therefore can you show that it is whatever they ask you to show. Alright, so from the equations, so the mole of HX over the mole of Na2CO3 is equal to 2/1. If you watch my other topical playlist on mole stoichiometry, and the mole concept, you will know that I like to set up my mole equation like this because I can never go wrong in this kind of bookkeeping, proper bookkeeping method. List out what I'm trying to say, and then everything on top refers to the HX. The first bit here is come from the balanced chemical equation. The second bit on the right will be the actual thing that actually reacts. So the HX is what I want to find the concentration, so I use square bracket to represent the concentration, times the volume of the HX used, which is 25.0 cm cube. So I need to convert that to dm cube because the concentration is in mole per dm cube, times dm cube. This will give me the unit of mole. This is also the unit of mole over mole. Okay, mole ratio, yeah. At the bottom bit there, so I also have the concentration of sodium carbonate, which is 0.500 mole per dm cube, given here, and I also have the volume of the sodium carbonate used, so there's 25.0 cm cube, convert to dm cube by multiplying 10 to the minus 3. This and this get cancelled out, so you can move your value around. So leave that on that side, and I can just move it on the left because everything is to do with equal. So this one can be moved up, so I will get 2/1 times 0.0500. This will give me 0.100 mole per dm cube. Therefore, this is shown as required. Alright. So next bit is asking us to state the acid dissociation constant, and you can only talk about acid dissociation constant for weak acid. So it turns out that HX is actually a weak acid, and you need it in terms of H plus and HX only. So if I write it for a weak acid, I will use equilibrium to represent a weak acid, as indicated by the value, the fact that we are doing a Ka means that it must be a weak acid, therefore it must exist in equilibrium, that it only partially ionizes into H plus in solution. So Ka is going to be the concentration of H plus times X minus over HX. But what are they asking for? They're asking for in terms of H plus, which I have, in terms of HX, which I have, only. Oh, I have X minus. So one of the assumptions for a weak acid is that the concentration of H plus is equal to the X minus, simply because this is 1:1 mole ratio, and that this is a monoprotic or monobasic acid as indicated here. It only dissociates once. Alright, so this is equal to, well, approximately equal to H plus square HX, because I can equate these two together. So now this is in terms of H plus concentration and HX concentration, both of which are in square bracket. It has to be a proper square bracket to indicate that it is representing concentration. The next bit, the pH of the aqueous solution is 2.43. So pH equal to minus log 10 of H plus. So therefore H plus concentration is 10 to the power of minus pH. So if I know the pH, I can work out the H plus concentration, which is this, mole per dm cube. Now I have concentration of HX. Do I have concentration of HX? Yes, I do. Concentration of HX is 0.100 mole per dm cube. HX initial is equal to 0.100 mole per dm cube, as they asked you to show earlier. So we have to assume that the HX concentrations at equilibrium is roughly the same as the Hx concentration initial, simply because when we are dealing with Ka, this represents equilibrium concentration. However, because very little of it dissociates, simply of it being a weak acid, okay, very little of Hx dissociates, such that the concentration equilibrium, due to very little dissociation, is going to be roughly equal to the initial concentration as given, as we were asked to work out earlier in the question. All right. I'll leave that being exact, 10 to the power minus 2.43, as I'll use it in the later bit of the calculation. You need to show pKa of the acid is 3.86. So perhaps I can start by showing Ka first. Ka from the previous part of the question is H plus square over Hx initial, because I have done this approximation for the second step, in addition to the approximation for the first step, which I've done there. Okay, so first assumption, second assumption, weak acid, Ka, yeah. So put that into your calculator, minus 2.43. I use that exact value, square divided by 0.100. So 10 to the power of 2.43 minus square divided by 0.100. I don't want to run up too much too early, so I'll run up to a more significant figure. I think this should be enough. 1, 2, 3, 4, 5, 6. All right. And then, of course, then pKa is equal to minus log 10 of Ka. If you have your answer on your calculator, you can just straight away press log 10 of that, and remember to take the negative value, and you get 3.86 exactly, and that is what they ask you to show. All right, so I got 3.86 just like that, shown as required. And as this is a show that question, you gotta show your working. And it's very easy to tell from the working whether you know your stuff or not, because some people do the wrong working and then they manage to show this. So, you know, it's quite a miracle. So all your working must be shown. As usual, label your working appropriately. You can write left and right as long as you label them properly, so that it's easy for the people who are marking your work to follow. You want to make their life easy, not make their life difficult. Don't have messy handwriting. Try to order things properly, yeah? So next bit, in an experiment, various masses of the sodium salt of the acid, so this is the salt of the acid, added to separate portion of the weak acid. So you're creating a buffer because you have a weak acid and you have a salt of the weak acid together. So you get a buffer solution. So buffer solution resists changes in pH as you add a bit of acid or base to it, right? So after each addition, you work out the pH, you measure the pH using some sort of pH meter. So it's a sensor that measures pH, so you can use something called pH meter. And there is the mass of NaX added, and there's the pH value. Do I need to... Oh, there's no processing data at all. Apparently it's just plotting a graph. So instead of me flipping back and forth onto that previous data page, I have opened up the data on another piece of paper, and I'll start plotting so that it doesn't hurt my eye, you know, flipping back and forth. You need to draw a curve because they say it's a curve. They already given you the axis label, the x and the y. It does not start from 0 on the y-axis, not that it matters. It's just so that you are always aware of what you are doing, yeah? So the mass of NaX added being 0, so when there is no NaX being added, is the pH of the weak acid is 2.43. This is 2.5, this is 2.42, so 2.43 would be rough. Nope, I could do better than that. 2.43 will be roughly there. 0.10 is 2.81. 0.10 is 2.81. 0.2 is 3.11. 3.11 is close to 3.1. 0.4 is 3.41. And 3.59 for 0.6, so there's no 0.5, yeah, be very careful, read carefully. 0.6 is 3.59. No, I can do better than that. I can still do better than that. Okay, so it's very important that you spend some time actually plotting the graph and practice your curve sketching or whatever, okay? 0.8 is 3.71, 0.8 is 3.7, 3.7 3.7 3.7 3.7 to 3.71. Actually just now 3.11 there's 3.11. This one is 3.7 3.71 3.72 3.71. What am I thinking? One is 3.81, one is 3.81. So 3.8, 3.82, so 3.81 is roughly there. 1.2 is 3.89, 1.2 is 3.89, it's roughly there. 3.99 is close to 4, so it's 1.5 and close to 4. Oops, 1.5 and close to 4. And then 2 is 4.11. 2 is 4.11. Okay, so I need to sketch a curve. This is the difficult thing about doing on the graph, is that can I do better than that? Maybe. I could go like this. Yeah, I can do better than that, I think. Yeah. So as you can imagine, if you have pencil and you do this, then you know it does take a while. So I'm like, oh, this is an even worse curve. So it's not really that great here. I don't know. I don't think I'll be able to get like a perfect curve. Anyway, it does take time for you to practice drawing that. Which one do they want? Circle one anomalous result. I guess if this passes through this point, so most of the points actually lie on the line. I think this one is the most anomalous. So let me try and redraw that. Nope. So most of my points are very close to the line. This is probably the most anomalous compared to this. This is only like 1 square away. This is like 1 square away. This is like 2 square away. I would imagine that this is the most anomalous, so I'll circle that. But I guess even if you think about this being most anomalous, you could have circled this and then reasoned them out. Alright, so I don't think there's just one particular answer. So it's not like extremely anomalous result. It's just that this one is it's just slightly more obvious than these two. But of course, I'm pretty sure that if you circle this, it will have been alright, as long as you come up with a reason that can account for why the points are above the line being shown there. Okay, so my anomalous point, give a reason. Okay, so the anomalous point circle above is below the line. So meaning to say they don't ask us to state which point it is, they just ask us to circle. It's below the line. What does it mean? It means that the pH should be there, but this pH for this particular reading at 0.2 mass or 0.2 gram of NaX being added is recorded being lower than what it should be. Okay, so the pH recorded is lower than what it should be. So what it should be is, if you follow the curve itself. Okay, so why is the pH recorded lower than what it should be? So you have a pH meter, right? A pH sensor. So if you take the reading too early, you know, like as the pH meter gets calibrated, and then you put it into the solution, and then you straight away read the reading, or sometimes you wait a bit and then the reading can change further. All right. So the fact that this reading is too low could be that either you took the reading too early. That might be one of the key reason, because with the more NaX being added, you see the pH of the weak acid slowly increases, right? I mean, become less acidic. All right. So that could be one of the reason. So this could be due to, I don't know, the reading on the pH meter or pH sensor was taken too early, and the fact that you took it too early means that meaning the NaX added might not have all fully dissolved. If you don't have all the NaX fully dissolved, then your buffer is not completely formed yet. All right, it hasn't equilibrated yet. It hasn't equilibrated yet, because, you know, like, not all the NaX has gone into solution yet. All right, either that, or you can say that actually, because the pH is lower than what it should be, maybe you did not add 0.2 gram of NaX. Maybe you actually add lesser than 0.2 gram. Okay, so that could be one of the reasons for why the point is below the line as well. All right. Of course, you could also argue that why is this point above the line? Because, well, you know, it should have been here, but it is here, meaning to say that you have added less. You have added you have added a bit too much, because this should give you point around 0.44. So perhaps you add 0.44, it will have given you a higher reading of the pH, when in reality you should have added 0.4 and get this pH instead. So I guess too much or too little of the NaX added could have affected whether your anomalous point come at above or below the line shown on the curve. All right, so a bit of thinking there, I guess. All right. More calculations now. So the graph shows that a pH of 3.86 is obtained when you have 1.12 gram of NaX is added to 100 cm³ of HX. Alright, so this is a solid. When you add solid and you add it to a solution, so your total volume is still 100 cm³. The pKa of the weak acid is also 3.86. So your pH is equal to the pKa. So when your pH is equal to pKa, there is something that can magically happen. I'll show you what I mean by that. Ka is H plus X minus the HX. Alright, so all this refer to the equilibrium concentration. But now, for a buffer, you have a lot more of the salt, not from the weak acid, but from the salt of the weak acid which fully dissociated. So essentially, I could approximate that to H plus equilibrium, X minus from the salt, and of course, very little of the weak acid dissociates. That's why the concentration at equilibrium, is roughly similar to the concentration of the HX initially. All right. So if you look at that, what you could do in reality is you could take a negative log of all of these, and then you will get this expression. I'll show you what I mean by this expression. So if you have done additional maths before, or if you've done A-level maths, you will know the rules of logarithm. This is multiplied, so you can add them together. But because I'm taking negative log, so it's negative and negative. But then when I do divide, it will become a negative. But I also take negative log, so it's negative, the log of that. That's why it becomes the positive log of the HX concentration initial. All right. So what do I mean by that? Minus log of Ka is pKa. Minus log 10 of H plus concentration is pH. and then I could very nicely have a plus. So I then combine these two together again. I will get plus 10 hx initial over x minus. Alright, so the pKa is equal to the pH. Look, the pH of 3.86, the pKa of 3.86. So as pKa equal to pH equal to 3.86, so this is equal to this, so the pKa minus the pH will be equal to 0. So 0 is equal to log 10 of hx initial over x minus. So when you have that, you can move the 10 to the other side, and you will have hx initial over x minus is equal to 10 to the 0. Anything to the power of 0 is just equal to 1. And then therefore you want to work out actually, what do you need? You need the concentration of the acid is equal to the x minus, and that is the initial, right? And that's just 0.100. Okay, so okay, I've used up all my space there. Perhaps I can move this a little bit to the left hand side. Alright, and then I can move this a little bit to the right hand side, hopefully. Oops, no, that doesn't work. So now that I've shown you, I guess what I could do is I could cut this method short, and then I can just say that is true. Okay, so that is equal to that. And then what else? I need to calculate the relative molecular mass of Hx. So we know that the concentration of the Hx is equal to the concentration of the salt. Alright. What do I need? What else do I need? So I have 0.100, which is the concentration of the acid. Initial is equal to x minus. So if there is 0.100 mole per dm cube, and what is my x minus? My x minus concentration is equal to the concentration of the NaX. Okay, so this is also equal to the concentration of NaX, because the NaX gives you the x minus. So what I could do is, what is the concentration of NaX? It's going to be the mass of the NaX divided by the this is not good. What is the MR of the NaX? Okay, never mind. I think the MR of the NaX is what I want to find, because then I can take away the Na and I can find out the X, and then I can work out the MR of the Hx. So that is mass over MR. They will give you mole, and I want it to be equal to mole per dm cube, so I need to divide by the volume. So there's 100 times 10 to the minus 3. Mass over MR is mole over volume in dm cube equal to mole per dm cube. So this MR referred to MR of NaX is equal to, so you can move things around. First of all, I can move this up there, and then that's equal to that. So that is equal to 1.12 over 0.100 times, I need to move this a little bit to the left hand side, times 100 times 10 to the minus 3. And I get 112. So therefore the AR of X is equal to 112 minus, there's one sodium there, and the sodium is 23.0 atomic mass. So that is 89 or 89.0. So therefore the MR of Hx is equal to 89 plus 1.0. I get 90 or 90.0 would have been alright. I'm not sure if there's an easier way to do this. There might be an easier way to do this, but thinking about how there are 3 marks and how they ask you to show your working and how they've given you pH and pKa. So a lot of students will have gotten stuck if they don't know how to manipulate logarithms, as you'll be expected from your A-level maths anyway, and all this relationship. And what I mean whether there's a shorter way is whether there's a shorter way from here or not. But anyway, I managed to work out the molar mass of NaX, and I work out the atomic mass of X, and I could just add the hydrogen to give me the MR of HX as required. So that was a bit long there. Anyway, so the calculator MR is subject to small experimental error. As usual in every single experiment, there are always experimental error. So suggest a structure for the organic. So it's an organic hydroxy carboxylic acid that best fits your MR data. Hydroxy means it has OH, it has alcohol OH. Carboxylic acid means it has COOH. And then my MR is 90, and I don't have periodic table, but I'm given the atomic masses there. So if I have OH and CO2H, so the MR of OH is 16.0 plus 1.0 is 17.0. As you could have used this information, 16.0 plus 1.0. So CO2H would be 12.0 plus 16.0 times 2 plus 1.0. So that is 45.0. So when you have OH and CO2H, you already have 17.0 plus 45.0, which is 62.0. So what are we looking at? We are looking at the difference, 90 minus 62. So 90 minus 62 give you 28, and we could just fill in between CH3, which is 15, and then CH2, which is 14. So that is close to 15, and 14 will give you 29. But bear in mind that CO2H is terminal, so it's at the end, and OH is also terminal or somewhere in between, which means that you will have one lesser H, and 14 plus 14 give you 28 exactly. So it does make sense for it to be something like this, for example. So I know there's 2 carbon, CH2, CH2, CO2H. So this could be one of the formulas. Of course, another possibility is if you have CH3 here, then you lose one of the hydrogen, this becomes CH3, then you have CHOH. That is also possible. So what I'm saying is also possible is CH3, CHOH, CO2H. Okay? And that's why this question is about suggest a structure, not deduce the structure. Based on the MR, based on the information, hydroxy and also carboxylic acid, and based on what we know about this fitting the MR, so both are entirely possible. Okay, so this is the last bit of this well, I don't know, it's quite an unusual second question for analysis and evaluation, because the graph was pretty direct and simple. There's no gradient calculation or anything, and that's why you cannot always expect there to be gradient calculation, because it's all about spicing up the paper 5 for students to avoid over familiarization. It's about the skill set and not about what you have done before, right? It's using about your knowledge, applying your knowledge from experimental experience. Yeah. Anyway, this last question, another method for determining concentration of the acid HX is to evaporate a sample of the solution and weigh the solid that remains. All right, evaporate the solution, take off all the water away, and then you weigh the solid that remains. Suggest 2 reasons why this might not be a very good method of finding the mass of solid HX in a sample of the solution. So what can we say? How would you evaporate? How would you take off the solution? All right, so suggest 2 reasons. So it's about suggesting again, so I can think of a couple. Let me just think this through. When you when evaporating, so assuming that we don't want to wait a couple of days to evaporate it, so we would vaporize it. When vaporizing the solution, it might spit. It might spit, you know, like when something is boiling, it can spit out, right? Okay, or spill out, therefore losing HX, so less accurate. So that could be one of the reasons. When you lose your materials, then the mass that you measure won't be accurate. Yeah, okay. The other problem is that HX is an organic compound. Organic compound on its own, it's a simple molecular structure. So HX has a simple molecular structure, obviously being a simple organic acid and alcohol, so it's not giant molecular structure or anything. So it can also evaporate away, evaporate or vaporize with heat. So if you lose HX again, you know, less accurate, right? The other concern is that the when you heat it too much, when you heat it too strongly, when heated too strongly, organic compound can decompose as well. Okay, organic compound like X can decompose or might decompose, and of course when you decompose, that means you no longer have this thing, therefore whatever mass that you get or measure at the end of the reaction won't be an accurate reflection of the actual mass that you want. All right, of course the other thing is that evaporation takes a long time. All right, so evaporation of the water or the solvent can take a long time. So this might not be a very good method, not because the mass is lost, but because it takes too long. So everything that we do in, at least in the school laboratory, it does not, we don't want it to be too long, but we don't want it to be too short as well, because too short of a time means too fast of a reaction, would mean that there's a greater error in time. But too long of a reaction time would also mean that lesser error, but you are not expected to stay like 3 hours, 4 hours, 10 hours, 12 hours in the school laboratory, right? So it's all about sensibility. So I provided more than 2 reasons here, and I guess any other acceptable reason would be okay as a suggestion as well. So I reached the end of this paper 5 tutorial. If you